spin, opposite. So if the spin is opposite to the momentum, it will have left-handed. Right? So here it is left-handed. So this is by not by definition, but by experiment. By experiment, all neutrino are left-handed and anti-neutrino right-handed. So left-handed anti-neutrino doesn't exist. Right-handed neutrino doesn't exist. Similarly, why electron is behaving in one direction is because only left-handed electron exists. Just like the neutrino, they are always left-handed. And you will see, to conserve lepton number, the left-handed electron is always coupled with a right-handed neutrino. Later we will go also in the lepton number punya problem. So this was measured by or determined by Goldhaber and others in 1958. So Goldhaber made a very beautiful experiment to determine the handedness of the neutrino. Why does this so-called handedness violate parity? Because you know, by parity operation, the neutrino, when operated by parity, will give the right-handed become left-handed. Sorry, the left-handed become right-handed. But right-handed neutrino doesn't exist. So this is what you call violation. What do I mean? Suppose you have a neutrino that is left-handed. So this is a neutrino. A left-handed neutrino, which is this one. Of course it exists, but now you operate parity on it. What you have is a spin is not affected by parity, but momentum. Yeah, from to the right you go to the left. But this one doesn't exist. So the parity should act here on this to give this, but that the one on the right doesn't exist. But you will see later that if you do a PC or a CP operation, you will have conservation. You have left-handed neutrino here, operated by parity. What do you have? Like just now, you have a right-handed neutrino. But now, so this is what you get, but now you add a charge conjugation here. Charge conjugation to a right-handed neutrino give you a right-handed anti-neutrino. Okay, so the neutrino by charge conjugation become an anti-neutrino, and this exists. doesn't exist. Of course, this one exists. So, if this parity is violated, but CP is not violated because this exists. Okay? Of course, later we will see in Keon and B meson, this CP is slightly violated, but that's another story because the mechanism of violation is still not really known until now. Now let's relate this with a pion decay. Say pi plus decay. What they found was experimentally a pion plus will decay into a muon plus its neutrino, almost 100% branching ratio. Okay. So this decay is very good because only almost 100%. That is the only decay. But 100% put almost, yeah, no. Why? Because the width, yeah, of this pi plus to decay to E plus electron neutrino divided by the width of the pi plus to mu plus neutrino of muon. This is roughly about 1.23 times 10 minus 4. So they're very small. 1 in 10,000. 1 in 10,000, you get a decay of a pion positive into a positron. They're very, very small. 1 in 10,000. Okay. So, in terms of the quark line diagram, I haven't teach you quark line diagram. Later I will do that. But to explain this phenomena, I have to show you that this possibility is shown by a pion here, pi plus, consists of in this quark line diagram consists of a U D bar. This pion here consists of up and anti down. You know, meson is consists of a quark anti-quark pair. Okay, so this meson. So through the mediation of a W plus, which is the gauge boson of weak interaction, it can split into nu E, nu mu, and E plus or mu plus. In terms of energy, actually, decay into E plus is preferable. Why? Because positron has smaller mass than muon plus, positive muon. So in terms of energy, actually this top decay is preferable. But when you do the measurement, you find that muon plus is preferable, almost 100%. So the question is why? So this this can be explained as follows. Transition rate. What is transition rate a measure of decay? This transition rate measurement comes from the Fermi theory. Walaupun Fermi theory is wrong in some calculation, but in case of transition rate, the Fermi theory is right, because it doesn't involve high energy phenomena. For example, cross section and collision. This is just decay. You don't need to do any collision or anything. So Fermi theory is okay for decay rates, and it is also quantum mechanical actually when Fermi started this the theory. So the transition rate is roughly about half from the spin 1 plus beta for a lambda positive, and half 1 minus beta for lambda equal to negative. So beta, as you know, is V over C, the velocity. So basically this is for E plus, the value of beta is roughly about 1 because it is very light, whereas for mu plus the value of beta is roughly about 0.28. So so what happened was let me check what is the aridicity. Equal and opposite. Okay, when this pi plus decay, what happened? It emit a neutrino, whether it is E or mu, with left-handed neutrino. See? Yeah, neutrino is always left-handed, and neutrino is always right-handed. So those neutrinos here are all left-handed. So what this other guy emitted on this side, they are also left-handed. Okay. Whether it is E plus or mu plus. So this is the transition rate is this formula, because it involves this left-handed guy. Okay. So if you use this formula, for E plus, beta is almost 1. 1 minus, say, 0.9, very, very small. Okay. That's why this transition is very, very small. Whereas this person, mu plus, 0.28. So 1 minus 0.28 is quite substantial. Okay. So the beta value determined. So you put this value inside here, formula to show why that transition to E plus is suppressed. So this explains why E plus decay